This episode of Between the Lines with FGI is brought to you by the American Society for Healthcare Engineering, optimizing healthcare facilities.
So it becomes really important for healthcare institutions and their design professionals to reference and refer to FGI because they may not be getting code compliant direction from the manufacturer of their system.
Welcome to Between the Lines with FGI, a podcast brought to you by the Facility Guidelines Institute. In this podcast series, we invite you to listen in on casual conversations related to health and residential care design and construction. Coming to you from Washington State is FGI's very own John Williams, Vice President of Content and Outreach and Chair of the 2026 Health Guidelines Revision Committee.
And coming to you direct from St. Louis, Missouri is Bridget McDougall, Associate Editor with FGI.
And we're here, as always, because we're curious about the design of health and residential care facilities. Today, we're especially curious about MRIs, and we've invited our good friend Toby Gilk back to talk to us again about MRIs. Hope you enjoy.
Toby, thanks for coming back with us.
My pleasure.
We had a hard time letting go of you from when we were asking you about all things MRI because we just weren't done.
Right. And I'm so reticent to talk about it myself. So
one of the things we didn't get to that we really wanted to ask you about was this idea of quench pipes. I know when I first came across the term and the guidelines, I had no idea what it was. And I think you were the person I came to explain it to me. So can you first, before we get into what the guidelines say about quench pipes, explain what they are in relation to the MRI machine?
Sure. Most contemporary MRI scanners, what powers the magnetic field is an electromagnet. And for any of us who made electromagnets back in junior high physics or chemistry class, where you take a length of wire and you wind it around a battery and you connect the two ends of the wires to a positive and negative terminal on a big battery, and you get current flowing through the wire. And when it flows through a looped wire, it generates a magnetic field. An MRI is exactly that. It is an electromagnet. That's what generates the magnetic field. Only if you or I had to pay the electric bill to continuously generate a magnetic field that is 1.5 or 3 Tesla in strength, we would go broke very quickly because that just consumes an enormous amount of electricity. So if we want magnetic fields that are that strong and we don't want to pay through the nose for the electricity costs to generate that, we're kind of stuck until superconductivity. And superconductivity is just this bizarre property of some materials that when you get it cold enough, the electrical resistance in the material goes to zero, which is completely counterintuitive, antithetical to the way we understand things, right? I think we've all had the experience of, Christmas lights or whatever, and we plug 47 strings of Christmas lights together and we run it through one skinny little extension cord. And at some point you're like picking up that extension cord and it's warm, right? And it's warm because of the electric resistance to the resistance to the flow of electrons going through it. Superconducting just means that resistance goes away, which means, curiously, if we could put electricity into sort of a continuous Mobius strip, never-ending circuit, right? We could put electricity in and we could disconnect it from the electrical source. The electricity just keeps going and going and going and going. It's a perpetual motion machine. It's the world's most amazing battery. And that's what the coils that generate the main magnetic field inside the MRI are. When they want to energize it, they essentially come to the machine with something akin to jumper cables, right? And they hook it up to the coils that are inside the body of the MRI, and they start pumping electricity into them. And once they get enough electricity in them that it generates the magnetic field that they want, they disconnect the jumper cables and they seal the whole thing up.
That is crazy. I'm going to add that to one of the things also I did not know. So, okay, giant jumper cables, totally normal. Yes, go on.
So the magnetic field, that 1.5 Tesla, that 3 Tesla, it is an electromagnet. It is generated by electricity, but it is completely disconnected from building power. So you can go and turn off every circuit breaker in the building. You can kill power to the entire city. The MRI will still be magnetic because of the superconducting property of the material that they use for the wires. And because if you don't have sort of the jumper cable setup, you can't energize or de-energize the magnet in a conventional way. Now, that poses some significant safety issues, right? If this thing is always magnetic, we can't unmagnetize it, right? What if somebody gets stuck to it? What if somebody's pinned against the magnet? So in order to have a plan B, there is essentially a mechanism by which we can make the material that's inside the donut-shaped thermos bottle, we can make that material no longer superconducting. Well, how do we make it superconducting in the first place? Well, we have to get it to about 450 degrees below 0 Fahrenheit. If it's a few degrees warmer than that, it is no longer superconducting. It becomes resistive material. And then all the electrons that are essentially zipping through the wire start smacking into things that convert some of that to heat, right? What a quench is essentially making the wire inside the MRI no longer superconducting, such that all that electricity that's in there, it encounters electrical resistance for the first time and gets converted into heat, right? So we keep the wire super cold in most MRIs by partially submerging it in a bath of liquid helium that is 450 degrees below 0 is the temperature that this wire needs to be. If all of a sudden some of this wire starts heating up, in this case, heating up means going to 445 degrees below 0, right? And that is hot enough that the liquid helium begins to boil off. More of the wire essentially becomes resistive, and it's a cascade effect, and whoosh, all of a sudden, all of this electricity that's in the coils gets converted into heat and boils off massive amounts of the liquefied helium that's inside the thermos bottle of this, right? Okay.
Steam, right? Doesn't it change its property from a liquid into a gaseous material because of that heat?
That's exactly what happens. If we're right at the condensation point, boiling point of a liquid, it's possible to essentially go from a liquid to a gas at the same temperature. The temperature of the material doesn't necessarily have to increase. You have to add a little energy into the system to allow it to undergo that state change. But you can essentially have, for the sake of discussion, 450 degree below 0 liquid helium and 450 degree below 0 gaseous helium, if it's right at that state change point, right? But 1 liter of liquid helium becomes about 8 liters of gaseous helium. So we have an 8 times expansion just going from liquid to gas. But it's still...
Where's that gas going to go?
Well, it's still 450 degrees below 0, and everything in the outside world is 500 degrees hotter than it. If it gets exposed to any atmospheric temperatures outside the MRI scanner, it's also going to undergo thermal expansion. And the thermal expansion is going to be about another 100 times the volume. If we have 1,000 liters of liquid helium inside an MRI and it wants to turn to gas, then we have 8,000 liters of gaseous helium, super cold gaseous helium. A container that's designed to hold 1,000 liters isn't going to hold 8,000 liters. So we build up the pressure. The quench pipe is essentially a chimney. There's a valve that separates the chimney from the inside of the MRI scanner, either a valve or what's called a burst disc, which is a membrane that when the pressure builds up enough, just poof, gets blown into oblivion, and then it's open to the outside. So when bits of the electric wire become resistive, start generating heat, boil off some of the gas expands, increases the pressure inside the thing. Either the membrane rupture disc goes or a pressure relieving valve opens up, and we start getting this escape of super cold helium gas out what amounts to a chimney. We call it a quench pipe. Anybody who's ever played with a fireplace or a wood stove or something like that, it functionally is the same thing as a chimney. So this gas starts escaping out the chimney, except now that it's encountering atmospheric temperatures, right? It has lived its life inside this thermally insulated, refrigerated container. And now all of a sudden it's exposed to 70 degree, 80 degree air outside. So it's going to be absorbing all of that thermal energy, and it's going to be expanding about another 100-fold. And so as it travels, the volume of the gas gets bigger and bigger and bigger, because as it travels and touches stuff that is atmospheric temperatures, it's going to warm up. And so as it gets bigger and bigger and bigger, you get these massive pressure releases out, whatever the end of the chimney is that goes out the side of the building or out the roof of the building. You're just going to get these massive steam whistle-like ejections of helium gas. Now, that whole process is called the quench, right? That's if everything goes the way it's supposed to. But it's worth noting that there are things, and I absolutely detest the term, but I think it's something that people will understand, called a spontaneous quench, that there can be conditions that cause the MRI scanner to spontaneously erupt, right? Now, those are rare, and providers need to be aware that you don't necessarily have to be in a dangerous situation for a quench to occur. There can be sort of what appears to us to be hand of God kind of moments where this thing happens, right?
Toby, I know in MRI rooms, there's this big red button that starts an irreversible process to do that quench. Can you describe that for us?
In those situations, if the person is in grave danger, the most appropriate thing to do in that moment is to go and manually initiates the quench process. Essentially, that big red button is connected to a heating element, like in an electric water heater. And that heating element is just sort of buried in the giant thermos bottle of the MRI scanner right next to this superconducting wire. And you hit the button and it sends electric current to the heating element, and it warms up. And as soon as it warms up a couple of degrees, it becomes resistive, and it starts the cascade effect that triggers the whole thing in kablooey.
So there's other things associated with that quench piping, that quench vent that are requirements in the guidelines. I imagine as you're describing this force of energy and gas moving through there, there's all sorts of hazards associated with that. It typically discharges on the roof, right?
Most facilities, yes. Yeah.
Mm-hmm.
Have you seen mistakes of the vent in the guidelines? It's called the cryogen venting point. But have you seen designs where that has been placed in a less than optimal location?
Yeah, the manufacturers of the MRI systems, those companies, essentially provide some bare bones kind of engineering criteria for what the quench vent, how wide it should be, what the material should be, what it looks like at the discharge point, all of those sorts of things. But after they give the engineering criteria, they're like, hey, we're giving you guidance, you hospital imaging center, you're responsible for hiring competent engineers that can actually take the general engineering guidance and turn it into a practical, solution kind of thing.
Implementation, yeah.
Exactly. There are as many different implementations of this as there are engineers who design them, right? And some of them are awesome and some of them are not. There have been problems that I've seen engineers essentially mix and match, right? We're going to use the GE quench pipe discharge detail because the last MRI project we did was a GE one, and we have that in CAD, and we can copy and paste it, and we'll use it for a Philips MRI scanner. Even if the design and engineering criteria don't match.
Problematic.
It can be depending. I mean, if you're taking a less conservative design and putting it on a more conservative needing system, yeah, that can be problematic. There are vendors out there that don't really prescribe in their engineering criteria complete weatherheads for the discharge. And so like wind-driven rain can wind up entering the pipe, the tube, the chimney outlet. And if that happens, any water or snow or precipitation that makes it into the end of that pipe up on the roof is essentially going to fall all the way down to where the MRI is. It's going to accumulate or rest, in some cases, right up against that pressure relieving valve or the rupture disc. And if it gets cold, there are quenches that are sort of immediate and sudden and really no opportunity for things downstream to get cold. But then there are other quench mechanisms where that escaping super cold gas can essentially freeze solid any water that accumulates inside the quench pipe. There was this MRI that quenched, and it had this rupture disc, which is a thin sheet of graphite that's meant to separate the inside of the MRI from the atmosphere of the quench pipe. And when the pressure builds, that thin graphite membrane is essentially supposed to turn to powder and get ejected out. And after this MRI quench that happened, the MRI scanner literally exploded. It blew open inside the room. And I was one of the expert witnesses, and we got to do sort of forensic evaluation. And we took apart the part of the quench pipe that has this burst disc. And what is supposed to be there in a quench situation is nothing. You're supposed to have this big open hole that all of the pressure can escape through. However, when we opened it up, there were a couple of quarter-sized holes missing in this thin graphite membrane, but it was largely intact, which should be a physical impossibility. That was very strongly suggestive that there had been water accumulated. And this particular magnet, and the way that it quenched, it had sort of the slow run-up. It wasn't like somebody rushed in and pushed the red button. This was a quote-unquote spontaneous quench. Was venting cold gas into the quench pipe, froze the water solid. The water essentially became like a block of reinforced concrete right up against the burst disc and held it in place, while the pressure inside the MRI scanner builds and builds and builds because it has no effective way to go out until kablooey.
I'm looking at what we have in the guidelines, and one of the things it says is that it shall be designed with weatherhead sufficient to protect against the ingress of horizontally driven rain. So, to your point, the guideline says that you have to have that, but doesn't say specifically how or how much.
Most of the manufacturers of MRI systems require quench pipes, and there are specific new magnets that don't require this. Of the manufacturers of MRI systems that require quench pipes, all of them save one have standard details that provide complete weatherheads. One of them has a detail where the quench pipe essentially comes up out of the root, turns 90 degrees, and then has a 45-degree cutoff at the end of the pipe. And
I've seen that detail.
It was industry standard for a long time until we discovered that it only takes about a 25-mile-an-hour wind to push a raindrop at more than 45 degrees from vertical, which means if you live in a part of the world where you can get rain and wind at the same time, it's not going to offer the guarantee of protecting against wind-driven rain. It becomes really important for healthcare institutions and their design professionals to reference and refer to FGI, because they may not be getting code compliant direction from the manufacturer of their system.
It's really interesting that you mentioned that, Toby, because in the guidelines language around MRI equipment protection and cryogen venting points, we repeatedly say things like, you shall do this in accordance with the equipment manufacturer's technical specifications. So we repeat that over and over again. But the thing about the weatherhead sufficient to protect against the rain doesn't say the equipment manufacturer. We pull that out separately and say, hey, it doesn't matter what your manufacturer says. You best be taking a look at this, right?
So just as an example, the MRI that exploded, it had that detail that I described that doesn't really provide sufficient weatherhead. It came up vertically, turned 90 degrees, and had a 45-degree chamfered cutoff at the end of the pipe. And in the forensic investigation, it became really clear to us that water had been accumulating inside that quench pipe over an extended period of time. There were multiple different rings on the inside of that quench pipe of water and bacteria or schmutz or whatever that was accumulated in it. And we could just see that the water level rose and fell with the rainy season or whatnot. And so, yes, you're absolutely right.
All right, I think that quench that you talked about probably caused some conditions inside of the room that were a little extreme. There's a new section of the guidelines talks about building and occupant protection, and it says we have to have emergencies exhaust and passive pressure relief, and it shall be provided in that room with accordance with manufacturer specifications. What does that look like?
Okay. So working from the assumption that a quench pipe may fail, right? It may, our chimney may not effectively convey all of the helium gas that we want to the outside. To say nothing of the fact that helium is a noble gas, the atomic structure of helium is so incredibly small that a lot of the materials that we think of as solid or impenetrable are essentially basket weaves if you're the size of a helium atom. And so we look at this solid pipe and we think, oh, anything that's in there has no choice but to go out the pipe. Well, no, some of it will essentially push through the walls of whatever material is trying to contain it. We know this more simply from if you've ever had like a latex party balloon, right? Floats great on day one. On day two, it's barely floating at all. And day three, it's laying on the floor looking kind of sad. That's because the helium molecules are so small that they can essentially push out through the latex under any pressure. So even under the best performing criteria or conditions, right, where the quench pipe works exactly as we have it designed, some of that helium gas will escape into the occupied space, right? So we want to have an exhaust system that can essentially pull that helium-rich air out of the room because it's not toxic to breathe it, but you get enough helium inside the space and it will begin to displace the breathable oxygen-rich air. And that's bad for the home team. So if we have an exhaust fan, even under the situation where everything functions exactly the way it's supposed to, we know that helium gas will get into the room and we don't want it to collect or accumulate in sufficient quantities that it starts displacing the breathable air. So we want an exhaust vent to try and get it out of there. But there can also be failures or partial failures of the quench pipe where we're not getting just sort of a little bit of the helium gas leaking in. We can get, rather significant quantities sort of bursting into the room and very quickly sort of filling up the room, pressurizing the room with this extra gas before they pass out. Yes. So in a situation like that, we're gonna go into the Wayback Machine, the FGI Wayback Machine here. So one of my first involvements with FGI, before I was on the Healthcare Guidelines Revision Committee, I got brought in specifically to talk about MRI and MRI safety, sort of a safety subject matter expert or whatever. And so this was 5 versions ago, something like that. At the time, I was so vocal about the fact that we needed to make sure that the doors to our MRI rooms swung out from the room, right? Because there is this potential that the helium gas leaks inside the room. And you remember it undergoes an 8-time state change from liquid to gas. And then it undergoes 100 times state change, or not state change, volume expansion because of atmospheric temperatures. So that 1,000 liters of liquid helium inside the MRI scanner, if we let it all out and let it all come to room temperature, you take the state change and the thermal expansion, and it works out to about 750 to 1. So that 1,000 liters of liquid helium becomes 750,000 liters of gaseous helium at atmospheric temperatures and pressures. So that's a lot. That's essentially 5 times the volume of an empty room, the general size of an MRI scanner room. So we have, that room is already filled with 1x atmospheric air, and now we're going to fill it with 3, 4, 5x additional of gaseous helium. We're going to pressurize that room. So in the Wayback Machine, when I advocated so vocally for outswinging doors, the idea was that if the pressure builds up inside the room, it wants to help the door open, it wants to push it open, and you get sort of natural passive pressure relief. Well, back when I was on my soapbox about that particular issue, most of the MRI scanner room doors, radio frequency shielded doors, had roller latches. They weren't positively latching. You kind of had to go in and shoulder check the door either opened or closed because it just sort of friction fit into the frame. And so with no latch, sure, you want the door to swing out because the positive pressure, there's nothing keeping the door closed. It'll push the door open and the pressure will escape and equalize. So an outward swinging door works perfectly well without latches, but because of risks of smoke and fire propagation, NFPA and other life safety standards have essentially made it really difficult to have doors in a hospital or institutional use group that don't positively latch. As soon as you introduce a latch into this door, now if the room gets pressurized, yes, in theory, if you can open the latch, the door will burst open and equalize the pressure. The problem is that pressure all getting translated into the latch and the catch mechanism. When I was a freshman and I lived in the dorms from my first year in undergrad, I lived with a whole bunch of miscreants who half of whom are probably in prison at this point. But we had this tradition of essentially going around and pennying people into their dorm rooms, right? Which is where you take a stack of coins, pennies, whatever. You have one person push against like the bottom edge of a door so it kind of bows inward, right? The door is still latched. And then somebody else slides a stack of pennies between the door and the door stop so that when the person who's pushing the bottom of the door takes the pressure off, the door is in the same spot, right? That all of that tension is still in the door and winds up getting communicated up to the latch mechanism. What does that mean? That means the person who's inside that particular dorm room can't turn the lever, turn the doorknob, because there's so much friction on the catch, between the catch and the plate. You've essentially locked somebody in their own room from the outside.
Prison that you did things with, they're running major companies. That's brilliant.
Right.
But the physics principle behind pennying somebody into their dorm room is exactly what happens in an overpressure situation, right? The room pressurizes, it puts all of this pressure onto the interior face of the door. And what's holding that in place? The latch. So if you imagine if pressure increases 1/2 pound per square inch inside the room, average hospital-sized door is about 4,000 square inches of surface area. If we have a 1/2 pound per square inch pressure increase times 4,000 inches of surface area, that's 2,000 additional pounds of pressure acting on that door, which essentially can only get absorbed in the hinges on one side and the door latch on the other. We're applying literally a ton of force onto this door. I have subsequently, now we're calling for some sort of open duct or pathway that pressure inside the room can escape to someplace outside the room, so that once we do that, it really doesn't matter which direction the doorway swings because the pressure relief mechanism is taken care of separately. So for magnets with quench pipes, we're really looking for 3 things, right? The quench pipe itself, that we engineer it in accordance with the manufacturer specifications up till we get to the point of discharge and weatherhead protection. And we want to make sure that irrespective of the manufacturer details, that we have complete weatherhead. The second thing is we want to have an exhaust fan. So in a quench situation, even under the best circumstances, some of that helium gas is going to get into the occupied space. And we want to get that out so people don't have to breathe it. And then thirdly, in a significant quench pipe failure situation where the room becomes pressurized, we want to have a pathway for that pressure to escape that doesn't involve the doorway coming and going out of the room.
So that could be a vent, an opening with some sort of waveguide. It could be a blowout plug, maybe, that when it reaches a certain pressure, it pops out, and all of that atmosphere has a way to get out.
Yeah. So when I've designed these sorts of systems, sometimes I will integrate essentially a passive pressure relief with an exhaust duct. And generally speaking, you wind up upsizing the exhaust duct to be able to move that kind of pressure, that kind of volume out easily. So it's ducted to the outside. I've done some where it just goes into a plenum space, and you can actually there are certain products out there that are low pressure explosion relief hatches that get used in like chemical refining facilities and stuff like that. And you don't have to get to massive blowing the building apart pressures before the hatch will release. So there are a bunch of different ways that it can be done.
And that's
I was
what
just
the
looking to
guidelines are
see
for.
does ASHRAE 170 follow along with this?
I don't believe that ASHRAE really touches on the specifics of cryogen venting. I think that's FGI really that defines the design criteria for that.
So we have a little bit of appendix in the 2022 guidelines, and the 2026 is going to show up in the handbook that says that superconducting MRI systems that use trivial amounts of cryogen don't require quench pipes. So help me understand, what would be a situation where there would be trivial amounts of cryogen?
So helium is a finite resource on planet Earth. We used to have what we thought of as a limitless supply of helium because of this huge national stockpile. Turns out it's not as forever long-lasting quantities as we thought. And there have been intermittent helium shortages with supply chain issues and that kind of thing. So the MRI manufacturers recognize that as a potential weak point in facilities' ability to keep their MRIs going. There have been a number of facilities that have had quenches, and because of service contractors' inability to get sufficient quantities of liquid helium, the MRI is down for a protracted period of time. No hospital wants that. So the MRI manufacturers have come up with new ways where the superconducting coils are cooled through heat exchangers. They don't necessarily need to be in direct contact with the liquid helium. There are new MRI systems out from most of the manufacturers that use between 5 and 20 liters of helium, which when we were talking earlier, I was giving examples of 1,000 and 1,800 liters of helium capacity. So 5, 10, 20 is chump change compared to all that. So for those systems, because they essentially are dealing with those trivial amounts of liquid helium, and they have their own containment system, we don't have to have the quench pipe.
It's the difference between an MRI machine that has a polite burp and an MRI machine that needs to clear the room every once in a while because they ate too much.
So one quick question. We talk a lot about explosion here, but helium is an inert gas, right? We're not talking about a flammable gas, not something from a fire safety perspective that we're worried about. Is that right?
That is correct. Yes, exactly. So this is pressure-related explosions. This is not combustion-related explosions.
Perfect.
And
So
I would say to anybody listening to this podcast, if you haven't gone on YouTube and looked at a quench pipe in action being set off,
Yeah, just
what's the
look up
terminology here?
MRI Quench on YouTube and you'll be treated to dozens of videos of
I saw one with a group of MRI techs, and they were decommissioning a machine. They got to hit the button, the big red emergency button. I don't know if that's what you do every time you decommission, but I've never seen a group of more excited people.
Yeah, it's the
Mhm.
thing you're never supposed to do, right? I mean, or only
Right.
supposed to do in critical emergency situations. Lots of MRI techs spend most or all of their professional career never having actually, been a part of one.
Oh, okay. So there isn't any sort of routine maintenance where you need to demagnetize the MRI and you do a quench or anything like that?
No.
It stays pressurized pretty much.
Yep.
It should for most of its life.
Yep. And in fact, if an MRI is essentially going to be resold on the secondhand market, they don't want to quench the magnet because quenching creates the thermal shocks that can wind up damaging the system.
Toby, in this world of codes and standards in the physical environment, we're always dealing with concept of safety, and we acknowledge that there's a whole lot of things that we can do operationally, and there's a whole lot of things the building can do to make the operational burden less. And when we talk about MRI safety, a lot of it is about building the building so that you don't have to think as much operationally. What's your perspective about how important is the built environment components for MRI safety?
It is hugely important, in part because once you get the MRI up and running, nobody wants to touch the built environment because that means interrupting patient care. That means interrupting the operation of the MRI scanner, additional expense, lost revenue, those sorts of things. So for many facilities, you got one bite at the apple, one opportunity to do this well. Please don't look at an MRI scanner as just another piece of hardware, and don't look at the design of these facilities as some sort of copy and paste commodity. The workflow, the efficiency, the clinical flexibility, the life cycle costing, the safety of everybody involved are really essential inputs to an effective design for MRI facilities. That's true throughout the hospital. And I don't mean to say that the MRI is the only place where design is really important. But because of the persistence of these risks in the environment, I'm of the opinion that it's just really super important in this part of the hospital. We have all kinds of new MRI devices. We've got MRI linear accelerators, right, that are getting dropped into radiation oncology programs. We've got neonatal specific MRI scanners that are getting dropped into NICUs. We've got PET MRI scanners that are getting dropped into nuclear medicine departments.
It's difficult to look ahead to the future, I know. What do you think some of the changes will be in the next cycle, which, believe it or not, will be the 2030 revision cycle?
Boy, crystal ball gazing in such a technologically complex area such as radiology imaging is fraught under the best of times. I think that we're going to see more of this balkanization of imaging services. I don't think that we're going to see the death of the radiology department, but I think that we're going to see a very significant erosion of the boundaries of what the radiology or imaging department is. I think we're going to see imaging linked to so many new and different and exciting aspects of healthcare. From a design standard standpoint, we need to make sure that we're building in the flexibility for all of these alternative applications of imaging and imaging related technologies throughout the enterprise and in places that we probably haven't even really appropriately imagined yet. So it'll be very interesting, and it's really going to demand of us that we continue keeping our finger on the pulse of where things are technologically, clinically, and in the business world of healthcare as well.
Imaging is ready to boldly go where no one has gone before. And the FGI codes are ready to go with it.
There you go.
See what happens. Yes.
Well, Toby, thank you so much for coming back and sharing all of this wealth of knowledge related to MRI safety. And I've learned so much.
It's my pleasure.
Thank you, Toby.
Anytime.
Thanks for joining us for another episode of Between the Lines with FGI. Do you have an idea for an episode? Or perhaps are you interested in sponsoring one or more episodes? Get in touch with us by sending us an email to podcast@fgiguidelines.org. Many thanks, as always, to Neil Kane and the Neil Kane Trio for the use of his song Skip to My Lou from the album of the same name. And please join us next time as we go between the lines with FGI. Goodbye, everybody.
Truly, truly. So fun. When you were talking about the frozen, the thing,